Initial value theorem. Initial value theorem of a Laplace transform enables us to calculate the initial value of a function f of t, that is f when t equals to 0, that is f naught, directly from the Laplace transforms, that is f of s, without the need of finding the inverse Laplace transform of the f of s. The direct Laplace transform of a derivative of d f of t by dt with the limits s tends to infinity, that is limit s tends to infinity, Laplace transform of d f of t by dt is given by limit s tends to infinity 0 to infinity d ft by dt e power minus st dt. So on the topic Laplace transform of the derivative, we found that this value equals to limit s tends to infinity of s of f of s minus f of 0 plus. However, when s tends to infinity, e power minus s tends to 0. Then this total value will be equals to 0. And this value is a constant, so we can write this as f of 0 plus equals to limit s tends to infinity of s of fs of 0 plus is equals to limit s tends to infinity s f of s. This equation permits the evaluation of initial value of the time domain solution f of t. It is then possible to work directly with the transform version of the solution to obtain initial values by performing the operation called for on the right hand side of the equation. And this equation can be stated as initial value theorem. The given f of s equals to this function, find the f naught, or find the initial value by using the initial value theorem. When you take on this, the formula is f naught plus is given by limit s tends to infinity s of f of s. Now limit s tends to infinity s of this function. So I'm taking constant m outside of it, s. I'm taking s out of this, then s of 1 plus a by s sine theta divided by, here I can take out s square of 1 plus a by s square whole square plus b square by s square plus b by s cos theta divided by 1 plus a by s square plus b square by s square, and this is s square. Remember, when you're evaluating for initial value theorem, the s will be here. That s should be cancelled, otherwise the total term will become the infinity value. So try to cancel out this s by taking the common from the denominator, so that this term will be cancelled. S square. Now substitute the value of s in the function, then m of 1 plus a by infinity 0 of sine theta divided by, here 1 plus 0 whole square plus 0 square plus b by infinity is again 0 cos theta divided by 1 plus 0 whole square plus 0 square. This whole term is 0, and this term will be getting sine theta and m. The initial value of the function is m sine theta. Final value theorem. The final value theorem of the Laplace transforms enables us to find the final value of a function f of t, that is t tends to infinity, that is f of infinity, directly from its Laplace transforms f of s, without the need of finding the inverse Laplace transform of f of s. In the same way, the final value theorem can be developed from the direct Laplace transform of derivative. However, the limit is now taken as s tends to 0. Then limit s tends to 0, Laplace transform of derivative, that is d f of t by dt is given by limit s tends to 0, integral 0 to infinity d f of t by dt e power minus st dt. Now when you solve this, you are going to get limit s tends to 0 of s f of s minus f of 0 plus. This is from the Laplace transform of the derivative, but here limit s tends to 0, integral 0 to infinity d f of t by dt e power minus st dt equals to 0 to infinity d of f of t. Now f of infinity minus f of 0 plus. Now equate the both, you are going to get f of infinity minus f of 0 plus equals to limit s tends to 0 s of f of s minus, since this is a constant number, you can write f of 0 plus. So f of infinity, which equals to limit t tends to infinity, f of t equals to limit s tends to 0 s of f of s. So final value theorem, f of infinity is given by limit s tends to 0 s of f of s. This equation is the final value theorem and is useful where the transform solution of a problem is available and the needed information is about the final or steady state solution. Given the S domain function, that is f of s equals to 2 by s minus 1 by s plus 3, apply final value theorem. So as per the final value theorem, limit t tends to infinity, f of t equals to limit s tends to 0 s of f of s. Let us find s of f of s. S of 2 by s minus s of 1 by s plus 3. So if this is the case of initial value theorem, we'll be taking the common from the denominator to cancel the term s. But whereas in final value theorem, we don't need to take s as common, then you can directly substitute the value of s, limit s tends to 0 of s of f of s equals to, now I will submit s equals to 0 in this equation, that 2 minus 0 of 1 by 0 plus 3, that equals to 2. So from the final value theorem, f of infinity, that equals to limit t tends to infinity, f of t equals to 2. This is regarding initial value and final value theorems. If this video is useful, please like, share and subscribe.